Hello, everyone. One thing every chemistry and physics course you take starts off with is usually something about unit conversions. So I thought I'd do a little introduction to unit conversions. The main secret with converting units is to remember that if you want a number to not change and you want to do a mathematical operation on it, you got pretty much two choices. You can add zero to it, which doesn't necessarily help, and you can multiply it by one, which also seems to not necessarily help until you think of some different ways you could define one. So that's what I'm going to do. I'm going to use that method to show you some simple conversions. And from there, we'll do several examples, and hopefully that'll make sense. I might put the prefixes, the SI prefixes in this video as well. We'll see how long it takes. Anyways, let me turn that over to my document cam. So one of the numbers you might run into in everyday life is the height of Mount Everest. Well, the height of Mount Everest, which there was a great story written about a couple decades ago, I think, but it's called Into Thin Air. And one of the things you definitely learn from that is that the height of Mount Everest is 29,029 feet. And actually, it's changed a little bit since then. But anyways, 29,029 feet was the height of Mount Everest. And in the science classes nowadays, we don't use the British system, which includes feet and pounds and seconds. We use the SI system, the System International, or the International System, what most people know of as the metric system. But the deal is, when we want to convert something, we can only add zero to it or multiply by one to it to really keep from changing its value, at least in terms of these what we call multiplicative units. So in this case, I got to think of one. What value of one can I use? Well, there's one. There's also 2 over 2. There's also pi over pi. But we can also get a little bit more abstract and think that there's also, I don't know, 1 foot equals 0.3048 meters. There's also 0.3048 meters is equal to 1 foot. So I think you can probably see where we're going with this. Obviously, these last two seem to be potentially helpful, but I need to be able to multiply by 1 such that the unit I have, which is, this is a symbol for a foot, disappears in the unit that I want, which is, say, the meter, and that's what I'm trying to convert to. I'm trying to convert the height of Mount Everest to meters. I want that unit to remain. So what I'm going to do is I'm going to multiply it by 1. I'll put my fraction bar up here, and then I just realized, since that's a foot, I need a foot in the bottom. Just like if you were, say, reducing a fraction that happened to be like, let's say 21/15. You'd say 21/15 is the same thing as 3 times 7 over 3 times 5. And since everything going on here between these fraction parts is multiplication and division, then you can actually cancel things out as long as they're on opposite sides of the fraction bar. So with that, I can cancel out the 3 and the 3, and I know that this fraction becomes 7/5, and I know that's done because both 7 and 5 are prime. So similarly, I can cancel out this foot with this foot down here as long as I put the foot in the bottom. And of course, this is just a number, but you got to remember that all numbers can be expressed as over 1. So we're just doing multiplication of fractions. And when you multiply fractions, it's always numerator times numerator. And then that's going to be over the denominator times the denominator. So now all I can do is find out which one of these factors works. Well, it's the one with the feet in the bottom, and the one with the foot in the bottom has 1 next to the feet, and it has 0.3048 meters in the top. And then all I have to do is multiply to get the answer. We can see here, basically what's going to happen is I'm going to take this 29,029 and I'm going to multiply it by 0.3048. When I do that, I get 8,848. 0.04 meters. Now, I had 5 sig figs here in principle, and I'll usually use 4 here. So technically, I really shouldn't be including these 2 digits. So I'll just call it 8,848 meters. So that's how we convert, for instance, the height of Mount Everest to from feet to meters. Another neat example that I like is my mom used to tell me that my mouth was running a mile a minute. And this one's kind of nice because I can allow you to see what happens if you have units that have a denominator unit and a numerator unit. So if we do something like 1 mile per minute, which is what the speed at which my mouth was running according to my mother, and she's probably right. I was kind of a pain in the butt kid. So anyways, I would like to convert this to say miles per hour. So I've already got miles on top, so that's wonderful. All I really have to do is go ahead and convert it to miles per hour. So what I'm going to do is again multiply by 1. So I've got to build a fraction that has a numerator that's equal to a denominator, but that has obviously a minute in the top and an hour in the bottom. So I put minute up here just to remind me that that's where it needs to go, and hour down here. Well, one of the results I know is that 60 minutes is equal to 1 hour. So I can write the 60 with the minutes and the 1 with the hour. And then I see all I'm going to do is take this 1 and multiply it by 60. Technically, I'm also dividing by 1 after I get that answer. But obviously, a division by 1 doesn't matter. So just like up here where the unit of the foot canceled out with the unit of the foot, right here, the unit of the minute cancels out with the unit of the minute, and it's just left with 60 miles per hour. Okay, so 60 miles per hour is a mile a minute. That's kind of an interesting result anyway. So all this time I could have been a smart aleck with my mom and said, yeah, 60 miles per hour. So anyways, that's not really where we're going with this. So now the next thing is, well, what is 60 miles per hour, say, in meters per second? So meters per second is a typical unit that we use in physics and even chemistry if you had a velocity thing in chemistry, but you usually don't. So let's look at that one. Let's say 60 miles per hour. So I would like to convert that to meters per second, but I don't readily memorize. I usually don't even memorize the 1 foot equals 0.3048 meters, but I do memorize a lot of things. And it's not so much that I took time to memorize them. It's just I've used them so much in my life. I know them. So like, for instance, I don't know the unit from miles to the conversion from miles to kilometers or anything like that, nor do I know the unit from miles to meters, so that's not very helpful. But I do know, for instance, the conversion from miles to feet, and I certainly know the conversion from feet to inches, and I certainly know the conversion from inches to centimeters, and then of course I certainly know the unit of conversion or the conversion information to convert centimeters to meters. So we'll go that way, and that's kind of useful too because it'll show you a way you can do it when you don't have the exact thing, but you have a path you can get there by. So I'm going to first write 1, and in this case, I'm going to try to first get rid of the hours. So there's an hour here, and I need to get rid of the hour because I want it to be meters per second. So I could go straight from hours to seconds if I knew that, and I do know that, but I think some people might not know that number off the top of their head, but once they hear it, they'll remember it. So I'm going to put hours to minutes first. Okay, and then that, of course, will cancel out the hours and leave a minute in the bottom. I know that 1 hour is, in fact, 60 minutes. And then now I make another fraction to get rid of the minute, so I have to put the minute up top. And now I want it to be seconds, so I have to put an S on the bottom. And this time I can see that the minute is going to cancel out with the minute, and I have miles per second. I happen to know that 1 minute is equal to 60 seconds, so that's the actual conversion. Now, if you look at it, you realize that ultimately, if we were finished right now, I'd multiply 60 times 1 times 1. I'd get an answer of 60. Then I'd divide it by 60. That would give me 1. Then I'd divide it by another 60. That would give me 1/60th. But another way you could do that is instead do 60 times 1 times 1 and then divide it by 3,600, because 60 times 60, just like 6 times 6 is 36, 60 times 60 is 3,600 because you have 2 zeros you have to put on the end. So that's a neat conversion that'll help you. 1 hour is equal to 3,600 seconds. and that's kind of interesting. And it also happens to come up again in physics and astronomy, because it turns out that 1 degree of arc is actually equal to 3,600 arc seconds, and that's the symbol for an arc second. So that's something else we have. But so far, we've now gotten to miles per second. Obviously, I've just figured out that 60 miles per hour is basically 1/60th of a mile per second. That's not that helpful, but anyways, I'll continue on. I'm going to now try to get rid of the miles. I do know that mile needs to be in the bottom. And I do know that 1 mile is 5,280 feet. So now I can cross out the miles here. Notice I'm using a different cross out thing each time. Doing that is good practice. It helps you keep from making mistakes, or if you do make a mistake, you'll see later exactly where it happened, because you'll notice, oh, I did the X with this, but it was supposed to be with that. So anyways, that will get me to feet per second. I also know now that I want to get rid of feet, I can do 1 foot is equal to 12 inches. And I can do that 1 inch is equal to 2.54 centimeters. I'm running out of space, so I'm starting to write small. That's not good. That's not professional at all. Okay. So finally, the last step, I can get from centimeters to meters by recognizing that I get rid of the centimeter down here by dividing by 100 meters, which is equal to, 100 centimeters, which is equal to 1 meter. So ultimately, what I'm going to do for all this math is I'm going to multiply 60 times 1 times 1 times 5,280 times 12 times 2.54 and times 1. Okay. Then I could actually just hit equals. And then with my calculator, I could 1 by 1 say divided by 60 equals, then divided by 60 equals, and then divided by 1 equals, and then divided by 1 equals, and then divided by 1 equals, and then divided by 100. Notice that's 100 centimeters here. This is 100 centimeters is what that is. So doing that, I would get the right answer. If you're not careful with that, you'll make a mistake. So what I tell students to do is either do it like that, where you hit equals each time after your division, or you have to, when you're finished doing all the numerators, you then put divided by and do a left parenthesis, and then type 60 times 60 times 1 times 1 times 1 times 100, close parenthesis, and then hit equals. If you do all that, the answer turns out to be a simple number that is probably not bad to keep on to keep in your memory, but it's 26.82. Yeah, 82 is good enough, I guess. 26.82 meters per second. So 60 miles per hour is about 26.82 meters per second. That's the typical speed we'll use like in a physics class, because that's the base units, the meter and the second. The base units in the System International is the kilogram, the meter, and the second. So 60 miles per hour is about 26.82. Doing this, by the way, I've used nothing but 100% accurate factors. There is exactly 5,280 feet in a mile. There's exactly 60 minutes in a second. There's exactly 60 minutes in a minute, or 66 minutes in an hour. There's exactly 5,280 feet in a mile, exactly 12 inches in a foot, and exactly 2.54 centimeters in an inch, and exactly 100 centimeters in a meter. So by doing this, I don't shorthand my significant digits at all. This one, you might argue it has 2 sig figs, so really we should be calling about 27 meters per second, and that's fine. Okay, so if I'm using sig fig rules, this either needs to be 30 meters per second if you had 1 sig fig, or 27 meters per second if you assume that to be 2 sig figs. So that's a pretty good couple of examples of converting units. There's another one that gets kind of tricky though, and I like the example of the density of water to do that. Oh, by the way, let me go ahead and do this too. Let's convert 26.82 meters per second. I'd like to convert that to kilometers per hour, because this is a very common thing you'll have to do. Is actually the other way around. You're normally given kilometers per hour, because if you watch Wimbledon or anything like that, you'll see that speeds are listed in kilometers per hour. So that's a common unit to have a speed in, and you would want to put it in meters per second to work in physics. So it turns out to be a really simple result. First off, we know that I want to get rid of the meter in the top, so I'll put meter down here in the bottom, and I know that there's 1,000 meters in 1 kilometer, so that brings me to kilometers per second. And then I also know that I want to get rid of the second in the bottom, and I know that there's 3,600 seconds in 1 hour. So clearly we can see that the meter canceled out with the meter, the second canceled out with the second, and I'm left with kilometers per hour. And of course that 26.82 is going to be basically times 3.6, and that gives me 96.55 kilometers per hour. So we've gotten a couple of different results here. One, 60 miles per hour, which is the same thing as a mile per minute, also happens to be equal to 26.82 meters per second, which also happens to be equal to 96.55 kilometers per hour. So there's some pretty good results that we've got there. Now for the other thing that I was talking about, which is the density of water, which is really one of my most fun conversions because it happens to have a lot of constants that we use in physics that you should know. And the coolest one, I think, is the fact that if you take a cubic meter of water, cubic meter, remember a meter is about 39 inches, which is about the height of a doorknob. So if you take a meter and make that the depth of a box, and then you make the width and the length of the box also a meter, then you have a cubic meter. That's a pretty good sized thing, 39 inches by 39 inches by 39 inches. But you're not going to believe it, but if you put water in there, that's in fact going to be what we call a metric ton, or a TONNE. And that's because the density of water is 1,000 kilograms per cubic meter. Okay, so a kilogram is typically about 2.2 pounds. That's actually an entirely different unit than the unit of the pound. The kilogram is a unit of mass, and the pound is a unit of weight. But for right now, I'll just tell you, near sea level, 1 kilogram is about 2.2 pounds. So a cubic meter of water has a mass of 1,000 kilograms, which is about 2,200 pounds. And you can tell, if you remember anything about tons, tons are supposed to be 2,000 pounds. This is a ton, TONNE, or what we call a metric ton, whereas that 2,000 pound one's called a short ton. So that's kind of interesting, just to know that a box of water that heavy would be that heavy. So now what we want to do is I want to try to convert this to grams per cubic centimeter. So you might think, wow, that's going to be kind of bad because, it's this big, huge 1,000 kilograms, and grams is going to be huge, but watch what happens. So first off, let's go ahead and convert the kilograms to grams. So if I want to get rid of the kilograms, the kilogram has to be in the, hopefully you all knew the bottom, okay? And I want grams on top. Well, I happen to know that there is 1,000 grams in a kilogram. That's what a kilo means, it means 1,000. So I'm going to multiply ultimately by 1,000, which looks like, holy crap, I'm already up to 1,000,000 grams. And that's right, but check this out. Now I want to calculate or convert this meters to centimeters. If I want to get rid of a meter that's in the bottom, then I have to put the meter in the top now. Notice how that's sort of different than most of what we've been doing, other than the hours and stuff like that in the denominators of speeds. So I put the miles up here, or the meters up here in the top, and I put the centimeter in the bottom, and I know that 1 meter is equal to 100 centimeters. But look, that's only 1 meter. I've got meters cubed here. That literally means meter times meter times meter. So I've got to do this 3 times, or I could cube it, of course. That's certainly reasonable. So I write 1 meter over 100 centimeters times 1 meter over 100 centimeters. So ultimately what I'm doing is I'm multiplying by 1,000, which is big, but then I'm dividing by 100 times 100 times 100. Well, 100 times 100 is 10,000, and then times 100, that's 1,000,000. So I'm multiplying by 1,000 and then dividing by 1,000,000. That's equivalent to dividing by 1,000. And notice, just like in this before, we did get finally, just like this did, we were able to get rid of the centimeters that were up here, and we were able to get rid of the inches that were down here. With that, well, the same thing happened here. This kilogram canceled out with this kilogram, and then this meter, and this meter canceled out with these 3 meters. So ultimately, I'm just dividing by 1,000, so that gives me the answer is 1 gram per cubic centimeter. So the density of water is 1,000 kilograms per cubic meter. The density of water is also 1 gram per cubic centimeter. And one other unit that's kind of helpful is what would this be in grams per milliliter? So if I take 1 gram per cubic centimeter, okay, and I want to convert that to grams per cubic milliliter, what I'm going to have to do is figure out what a liter is. So it turns out the definition of a liter is defined to be a box, a volume of a box that's cubical. It's a cubical box whose width is 10 centimeters, whose height is 10 centimeters, and whose length is 10 centimeters. I think you all know the formula for the volume of a rectangular solid, in this case a cubic solid. It's length times width times height. So we're going to do 10 centimeters times 10 centimeters times 10 centimeters. It actually equals 1,000 cubic centimeters. So that's what the definition of a liter is. So a liter is 1,000 cubic centimeters. So what I can do, and you'll see later that there's a much smarter way you can avoid all this work. What I'm going to do is say that 1,000 cubic centimeters on the top, because I want to get rid of the centimeters in the bottom, is equal to 1 liter. So that's going to make it up to 1,000. But then I'm going to take and say that 1 liter is equal to 1,000 milliliters. So duh, you should have thought from the beginning, if this is 1 liter, which is 1,000 centimeters, then 1 milliliter should be 1/1000th of this, which would be 1 cubic centimeter. So we actually discovered something new. One, we found that the density of water is also 1 gram per milliliter, and we found that 1 cc is another name for it, 1 cubic centimeter, is defined to be 1 milliliter. So they're identical. So the cc's that you hear about, if they're talking about the engine of a motorcycle or even the engine of the old Volkswagen Beetle, the Beetle was a 1,500 cubic centimeter, and I think the Super Beetle was 1,800 cubic centimeters, so slightly bigger. That's what they're talking about as cubic centimeters. So cc is a cubic centimeter, whereas a milliliter is the exact same unit, exact same size unit, but it has a different name. So we now also have learned the density of water. If you wanted to talk about salt water, it might be 1,025, 1,029. I've even seen 1,022.5 kilograms per cubic meter. So that's the only difference if you go from water to salt water. One other thing, it turns out that the density of air is actually about 1/1000th of the density of water. So the air in a room, since it's roughly 1,000, you'd say, oh, it's about 1 kilogram per cubic meter. Turns out it's about 1.29 kilograms per cubic meter. Actually, that might be what I was thinking of earlier. Yeah, 1,000 kilograms per cubic meter is supposed to turn to 1,025 for salt water usually. Of course, if you're in the Great Salt Lake or the Dead Sea, it's quite a bit higher than 1,025. Now, the other thing I was talking about was exactly correct. The density of air runs, I mean, it varies obviously with temperature and pressure and all that good stuff, but it's roughly 1,000, 1/1000th of the density of water. And I'm telling you, I always use the figure of 1.29 kilograms per cubic meter, but you might find 1.225 or 1.25 or something like that. So those are all fair. So I apologize for leading you into those errors. Let me write them down correctly. So density salt water is on the order of 1,025 kilograms per cubic meter. So that makes that a little more straight. And of course, the density of air varies, of course. So it might be 1.29 kilograms per cubic meter, or I've even seen, like I said, 1.225 kilograms per cubic meter. So those are all some interesting facts, and just in case some of this was blurry, I'm going to give you a little bit better view of all the calculations we did, all the numbers, slowly, and then y'all can pause it at any time you want. So hopefully this gives you everything you need. And there's those tidbits I gave you before. The density of salt water is probably about 1,025 kilograms per cubic meter. I mentioned the Great Salt Lake and the Dead Sea would probably be much higher densities. The density of air is maybe somewhere between 1.23 and 1.29 kilograms per cubic meter. So that's it. That's the whole spiel on unit conversions. I'm going to go ahead and kill this and just remind you before I do that there are other types of unit conversions. For instance, there's a linear conversion between Celsius and Fahrenheit. There's a linear conversion between Roentgen and Fahrenheit. And then there's just an additive conversion between Kelvin and Celsius. There's also a logarithmic conversion between sound intensity and decibels. Stuff like that. So there's a lot of different ways you can convert units. Maybe we'll do some of that stuff later. Have a good day.